Hello, everybody. We have like 20 participants. That good. Okay, let's see. How do we start tonight? How are you guys doing?
Doing good, Professor. How are you?
I'm doing good.
We're doing good. Thank you, Manasha. So how did the first lecture looks like? Any feedback from anyone?
It was pretty nice.
Yeah, it was pretty nice. Yeah, it was information that we had to note down. There was a lot of information, but I think it was
Right,
manageable.
right. Hey, for others like Paul, Christian, William, Sai, Ariba, not Kevin, Vincent, those guys doesn't have a profile picture on. Can you please make sure you have your profile picture on the Zoom account? Yeah, if you don't want to turn on your video. Thank you very much, Vincent. Yeah, of course, I understand that. Yeah, some may have the bandwidth problem, and with this pandemic season, like many of you probably are like working off the same network, like with your family member, that can squeeze your bandwidth. But if it is possible, then please turn on the video. Otherwise, please make sure you have your profile picture on your Zoom account, so that at least I can start mapping your name to your face. Otherwise, it becomes a faceless class, which is not good for me. Okay, all right. So let's start with maybe a little 5-minute breakout room, and where I want you guys to discuss among yourself about this lecture, and if you have any difficulties in concept and can help each other, or if you have some question that you can ask me after you come back from the discussion session. So maybe I will put that, maybe I'll put 10 minutes to have a chit chat, light chit chat, and about these courses or any other issues that you can have. But I would advise you to mostly focus on this lecture one, and how did it go? What is the difficulties you faced? And if you have any conceptual question that you need to ask your peer or any other thing, please go ahead and do that. And then we'll come back to the main session, and we'll again do a walk around that if there is any question for me that I need to answer and resolve your concept. All right. So let me start a breakout room. I haven't started recording yet because I know I'll just go from the breakout room from the beginning. After that, I'll start recording the sessions. All right. So breakout rooms. How many are there? 29, 28, 7. Grade 7. Let me put 10 minutes on the initial discussion. All right, open rooms for all. All right, let me start recording on now from the session. And is there any interesting questions from the discussion came up for me? Or non-interesting question?
Professor, I
so-
had a question. Oh, you want to go
Oh,
first?
sorry, Manasha, you can go ahead.
So I was watching the lectures and I was a little confused on the concept of IO mapped IO and then memory mapped IO. So if you could
Okay.
briefly
So
go over that.
just think in this way. In earlier days, when computer was built up, they are basically very less efficient, less powerful, and there ought to be like a 8-bit computing system. Means all the values you can represent is just 8-bit long, which is not much, right? It's 255 or maybe 16-bit, which is even not much, like 4 kilobyte total information. So that and like microprocessor or computer need to use addresses, unique addresses to address specific devices and the memories. Now, that means computing system need to produce some value. Addresses are nothing but values, which is either 16-bit, 8-bit, 32-bit, etc. Since the number of limitation, there is number of limitation on the bits, then it cannot address many things in the memories. If we include the memories are basically a lot of addresses, composed of a lot of addresses. And on top of that, if we want to make those values some assigned for addressing the peripheral devices like mouse, keyboard, etc., it is not very efficient at that point. Like it becomes like you have less amount of values assigned for the memories. Some part becomes addresses of the peripheral system. So to overcome that problem, a special line called IO or memory, IO and memory, that is produced from the processor, which indicates that, hey, I am giving a value, and this address value is for peripheral device, and this address value is for my memory device. Then corresponding that device will act accordingly. Now let's look at the modern system. It is at least 32-bit long, if not 64-bit. I believe all your laptops and everything now is at 64-bit, which is a huge number of address spaces. That means we can pack in addresses of the peripheral device along with the addresses of the memory together in the same number space. And we don't need that special line to indicate whether that address generated is for peripheral device or for the memory. So that's why in the modern system, you don't see anything special line which indicates an address for the peripheral or the memory, and it's called a memory mapped IO. Means memory address as if processor is writing on the memory address, but it is writing or reading, whatever that operation is, but it is actually interacting with in terms with the peripheral device. Same mechanism. It doesn't need to do anything special. So from processor point of view, processor thinks everything is a memory. Nothing special need to be done for the IO on the peripheral device. It's only some part of the memory address is connected with the peripheral devices, and in turn they are got manipulated. But the older system, since address space is very limited, a special line was created and processor need to be aware of, like if it is an IO operation or if it is a memory operation. And according to that, it need to send that signal. And that's the IO mapped IO.
Got it.
Make
Thanks,
sense?
Professor.
Okay, anything else for me? All right, let me do one thing now. Let me give you another picture or perspective about computing system and try to explain that how, if you write a small program, how it got executed inside a computer. It's basically gist of everything that you are going to learn in details in CS47 and CS147. Okay, so let me give you that overview to you. Okay, am I recording? Yes, I am. Let me share my screen. Okay. How do I present? Okay, so let's start with this memory. Memory, you can think of it as an indexed storage. I believe all you have done in the programming to define arrays and manipulate arrays, right? In the high level programming, like integer array 10 means a array of 10 element of integer element, right? Everyone familiar with that, I believe? Okay. So you can think memory is an index storage like the array, but in an electronics device term. But ultimately it's an array of like a storage like an array, and it is indexed with just like the array, indexed with the numbers 0, 1, 2, etc., etc. And these numbers, this index, what we call index in the software, we call memory address in the hardware. But it's practically one-to-one correspondence. It's just an array. And then what happens if that is an array? Let's talk about the MMU, memory management unit. Just think of this as a character. This is just a human like us. And what it does, we'll talk about that in a moment. But this MMU and this blank scratch pad index array together is called a memory device, electronic device, which called act as this storage. Now, what it does, if I instruct this device that, hey, write number 5 at address 3, what it will do, it will just do that. It will go and write that value 5 in that index 3. Very simple. Now I tell him write 13 at address 1. What it will do, it will just go and write that value in that address at that index. Just like a program. You can write a software program like that, of course, I imagine. Then we call this instruction read at 1, means read from address 1. So what it will do, it will go and look at that index 1 and retrieve the value and give it back to us. 30, just answer 30. So this is very simple. This is very simple model. And that's what we can imagine a memory to be always, okay? So that's one component. Another such component is ALU, okay, ALU, arithmetic and logic unit. What this character does is you ask it, okay, what is a 3 plus 5? It's an electronic component. We'll see, we'll learn how they generate these answers later. That's not a point, but what it will do, it will ultimately give you an answer back. That's what the purpose for the ALU is. So that's another component. And then another component is a register file. It is nothing but a glorified memory. What I mean by glorified memory, as an electronics device, this is really, really fast device, really fast compared to how that memory is, okay? But it is the same concept as the memory. It has some spaces, indexed array inside it, but it's a limited in number, and memory can have like 255 megabyte of space or 1 gigabyte of memory, that big chunk. But register file usually is limited to 32 or 64 or 128, something like that, around that, not even 1 kilobyte, okay? But these are the very fast in operation, and we call it a registered file, and corresponding character that controls read and write into it is called a register file unit. Now what it does, just like the memory, we can ask it to write something into the array inside it, or read something from it. Okay. Now comes our main part, controller. This is the one which is basically, I would say, heart and brain of the whole computing system, that uses these three basic components: memory, register file, and ALU, and make your computation happens. And this is all you have inside your processor. Your processor, in a very broad sense, comprised of controller, arithmetic logic unit, register file, and your computing system consists of mainly processor and memory. All right, so far so good. Question?
I have a question, Professor.
Yes.
So how does the system know? So like when we send something, right? How does it know like which memory to kind of store it in? Does it store in the actual memory, or does it store in the register file, or both?
That's a very good question, Manasa. Let's wait and see. Okay, let's wait and see, and we'll find out. If it is not answered, please ask me back. All right.
Sure.
Okay, now let's see. Okay, now let's talk about a very simple program, like an integer a equals 10, integer b equals 20, integer c equals a plus b. Right? We all agree this is a very simple program, right? And we can let to that, and hold on. What happens? Just a minute. I'm just messing around my screen a little bit. All right. Now, if you write this high-level program, which language doesn't matter. Like it can be Java, it can be C, C++. I'm just giving an example in C. Whoever is familiar with that, I think Java looks very similar. If you script in Python, that would look very similar. It is just not that there is a type variable. It is not a type variable. That's a different story, but this is a high-level program. Now, from there, what happens is this. First of all, these are the constants, right? A10 and B10 is a constant, and C is a manipulation, mathematical manipulation out of A plus B, and being stored in a variable. Now, any high-level variable has a correspondence in the memory. So that correspondence is done by a tool called compiler. I hope you guys are familiar with the tool compiler. Maybe yes, no. Java world, it is not that too apparent. In C, C++, it is apparent. Okay, there is a tool called compiler. It can be an runtime just-in-time compiler. It can be an interpreter, doesn't matter. But ultimately, at the end of the day, all your high-level variables are mapped to the certain address inside the memory. So they have a correspondence. So let's say some tool like compiler or system decide that, okay, A will be at address 0, B will be at address 1, and C means at address 2. So that correspondence is done. And also compiler breaks this down into very simpler steps of instruction, like write 10 to the 0, write 10 to 0, write 20 to 1, read from 0, read from 1, etc. We'll see what are they step by step. But it is broken down. Your high-level program is broken down into multiple simpler steps. Why? As you have seen, these components can do only simple things. Like for example, memory can do either write or read. ALU can do only computation, mathematical computation, nothing else. Thus the register file, it can only do read and write. That's all, right? But this whole computing system with these basic operations, combining them can do magic, like Facebook, Google, your video streaming, everything boils down to this simpler operation at the end of the day. So this is a very I would say, very exciting, very fantastic idea that something so simple can raise a very complex system like this video streaming system or Facebook or social medias or anything complex you can think of at the application space. But it all starts with these simple steps. Now let's look at the steps. First of all, these simple steps are expressed in terms of something called a machine code. Because computer is an electronic system and it does not understand anything about high-level instruction. It doesn't understand integer equal to 10. It doesn't understand write 10 at 0. It only understands something in values, which we call a machine code. So they are somehow translated to the machine code, and we'll dig deeper later into that, how and this type of code step by step creates a machine code for processor. We learn that. But let's say somehow it does it, and the tool associated with it is called an assembler. So assembler is a tool which translates this part into machine code, which a computing system can understand. Now the question becomes where this machine code goes. These machine codes are part of the memory. So when you start a program, start executing a program, its corresponding machine codes are loaded from the hard disk onto the main memory. All right. So this is how it goes. So let's say this program goes and being sitting down from the memory address 3 to 8, because there are like 1, 2, 3, 4, 5, 6, 6 steps to deal with. So these are the machine code, and controller understand this machine code. How does it understand this machine code? That's not a problem for now. We will be dealing with that in CS147 course, computer architecture course, how it understands this machine code. For time being, just assume it understands what to do. Yes, Sai, you have some question.
Yeah, I was wondering, is the assembler the same thing as the address? Because I remember in your lectures you said like each thing has an address, and that's how the processor knows to or the IONM knows how to give it where to
Assembler is not the address. Assembler generates those codes and it knows the memory address where is what. So something, your program goes here, your IOs are here, your data memories are here. So assembler is a tool itself.
Oh, and the address is actually the 26, the number?
Yes, addresses are these, like this index number.
Oh, addresses are the indexes, not what's inside the index?
No, not with the inside.
Oh.
These are the addresses, like 0, 1, 2, 3, etc., all the way to 9999 in this example.
Okay.
Okay, these are the index of the array that you can think of in terms of software.
And the assembler generates that.
And assembler generates this machine code and place them in a certain address, certain location in the memory. Okay. Is that clear, Sai?
Yeah, I think that makes sense.
Okay, all right. Any other questions from anyone? All right, now let's go and see what controller does. Controller has certain tools. For example, it has some scratch pad called PC or program counter. And all the processor start from a default address. So when you switch on your laptop, your Intel processor start up from a specific address means they have a program counter and it knows where to fetch the first instruction. In your case, when you boot up a laptop, in your case, it is a boot address. So it's the initial address where it starts booting your system. Let's not worry about that complex thing right now. Let's assume in this system, your startup address program counter holds a value 3, means when you power on this whole system, it starts with 3 by default, okay? Now, what the controller does, it asks the memory, hey, read from 3. So what memory will do? It will return this number, right? This is a machine code for controller, for the processor, and which supposed to do a write 10 at 0. Now what controller will do, it will immediately tell memory, hey, write 10 at 0. It can decode this number, knows that, okay, this instruction is saying me to write the value 10 at address 0. So it will simply ask memory to do that, and memory will obey it. So you see, integer a equals 10 just manifested into the memory. It becomes a equals 10 because we are assuming this address 0 is corresponding to a, variable a here. All right. Similarly, now what it will do, it will, okay, before that, after this step, remember the program counter automatically goes into 4. It increases up. Okay. Now controller will ask memory, hey, read from 4. So what memory will do? It will read from the address 4 and return back to the controller, this machine code. And this machine code, controller decodes it and know that we are trying to write 20 at address 1. So it will go and do that, is give that instruction to the memory, and memory will obey it. Memory will write 20 there, and our program counter will bump up to 5. Anshul, yes.
So just to clarify, so is what happens, so when you have all that code, then the machine stores all the machine code into slots of memory, like
Yes.
what you have in 3 through 8. And then when you run the program, it retrieves each individual slot from that memory and runs that. And then if there's any values created, then it stores that into separate memory slots.
Yes. Yes.
Okay.
Exactly.
Okay. So each like line of code, or each line of code is stored into the memory first, and then it's run.
Yes. Exactly.
Professor, I had a quick question as well. So your program counter, it starts at 3 in this example. Is that because 0, 1, and 2 are already like reserved for the programs? So the PC will always start?
Yeah, we can think that way. Just I want to have a simplified diagram for these. Later we'll see a specific part of the memory is assigned for your program. So no data goes there. And another specific part is assigned for the data. So basically it is predefined for a system. So this is just for this example. Assume that this is my data part, 0, 1, 2 is my data part, and rest of them are program.
Okay, I see. And is the program counter, is its main use for keeping track of where you are, like what step of the process the computer is in?
Exactly.
Okay.
Exactly. It basically indicates the what is my next instruction. Where is my next instruction I need to fetch from? Where is that in the memory?
Okay, thank you.
All right. Okay. Now let's move forward. So you know what is the next deal? It's basically read from 5. Memory gives back the machine code. Now memory needs, controller knows that, hey, this instruction is trying to read from the address 0 and store at the register file 0, right? So what it will do, it will first ask memory to do read from 0. Memory will return 10, right? 0 is 10. And then it asks the register file unit to write 10 at 0. So what will happen? 10 will go there in the register file. And your PC moves up to the next instruction address. Again, it fetches the instruction, gets back the machine code. That machine code said read from address 1 and store into register file 1, that address. So memory gets back 20, gives back 20 to the processor. Then controller says to the register file unit, hey, write 20 at address 1. So register file unit will write that. Now it fetches the next instruction, read from 7, read the machine code. And now it knows that we are trying to fetch from register file 0, fetch from register file 1, add them up, and store the value back in register file 2. So what it will do, it will ask register file unit said, hey, read from 0 and 1. What register file unit do, it will give it back two numbers, 10 and 20, because it's from 0 and 2, 0 and 1 from the register file. Then it will ask ALU that, hey, what is my 10 plus 20 looks like, because that's what I'm trying to, user is trying to do. ALU sends back, okay, this is 30, answer it back. And then it gives the register file unit said, hey, write 30 at the address 2. So it writes that value to the address 2 of the register file. Now it moves on to the next instruction, read from 8, get the machine code. Now it says that, hey, read from the RF2 and store it at 2. So what it does, it asks RFU to have it read from the address 2. RFU gives you back 30. It asks memory to write 30 back into address 2. That's where it is. And now see, the address 2 corresponds to variable C. That means we just executed till this part of the high level program. Make sense? So imagine, like, this is a very simple program, right? 3 lines of high level code, and we are discussing for 20 minutes or all different steps. They're simple steps, very simple, right? Take from memory, okay, understand what is going on, what needs to be done, instruct RFU or ALU to do accordingly or memory to do accordingly. That's what the controller does. But these steps are real steps. A processor follows these steps over and over again. Why we don't apparently feel it? Because processor is really, really fast. It is a very fast operation. Like, we may take like 20 minutes to discuss the step. It will take probably less than a millisecond to execute this part. All right. So this is so fast. Now, any questions so far?
I have a question, Professor.
Yes, Manasa.
So in a high level program, we said int A is 10, right? And int B is 20. If you replace the 20 with the 10, right? Then will it, now int A and int B have the same value. So when the algorithm gets converted into machine language, does it generate the same code, the same number, or would it be different?
Integer A and integer B has the same value. From a compiler perspective, they're still a different variable, means different memory storage location. So it will still create two different instructions.
Oh. So is there like a possibility where two exact same codes can exist? Can that ever happen?
For two different instructions?
For two different instructions, yes.
No, it is not it is not possible.
Okay.
There is a conflict, basically.
Got it.
Okay. Any other questions?
For the counter, how does it interact with the controller? I mean, does the controller tell the counter to increment every time it finishes a task, or is it based off a clock cycle?
That's a very good question, Zaid. So it has though I'm showing them as a kind of a discrete elements there inside the processor, some controller, some program counter, but from hardware perspective, they're all electronic component and they're connected with each other. And since you brought up the clock, yes, per clock, it increases the program counter. So your program goes in a linear fashion. However, probably that gives you the next question, probably will rise in your mind, that how then, if my code has a if or while, that is means a decision-making point where program branches, how does it work? How does it, because it cannot be sequential anymore. It needs to jump over some instruction and go into the other instruction. There are assembly construct to do that assembly program, like where you can decide and jump. Now, how really in the hardware it is done, you need to wait till 147. That's where we actually develop this whole hardware system, whole processor, and we'll try to understand how that mechanism works, how controller knows, and how it interacts with the program counter if it is need to sequentially update, or you need to update to some other values to fetch another instruction from the another address. So Jay, so keep your inquisitiveness up till 147. Sorry for that. This is out of our scope now. What you asked, very advanced question there.
Okay. Yeah, it's very interesting.
Yep, this is interesting piece. So everything, every complex engine in the world you can think of are running out of these very simplistic steps. But it doesn't appear to be like that sluggish or anything like that, because this processor are electronics component and it can operate really fast in the scale of nanosecond. Nanosecond is 10 to the power minus 9 second. So that's the scale of operation. All right. Okay. Now the next part is that I'm showing you right now in terms of some very high level English language like concept, like write 10 at 0, everyone understanding. What does it mean? It has a corresponding assembly code that looks like this. We'll learn to write this code. This is exactly reflect this program. All right, exactly reflect this code. And your compiler actually compile this code, something like this assembly code. Your assembler picks up this assembly code and generates machine code like this. We'll learn that, okay? How to write this piece of code, how we can convert each of these code into the machine code, we'll all learn in our successive lectures. Okay, question?
Professor, I have one more question.
Yes.
So now, after this 10, 20, and 30, right, they're stored in the main memory, then what is going to happen to them in the register file? Is it just going to delete those values?
It is still there. It is still there.
But isn't it like temporary storage though? So how long will it
Yeah,
be?
this is a temporary storage in the sense that it can get overwritten anytime, depending on your program.
Oh.
Yeah. Even memory is temporary. Like some program can step into the other variable and override that. Means like, let's say if you have another line called after this, another line called A equals C plus B. You can have it, right? So what it will do, it will calculate that number and override the memory address corresponds to variable A.
Got it.
Okay. All right. Now, what is that time? Let's take 5-minute break and we'll come back after 5-minute break then. All right, I think our 5-minute break is up, and let's see what we can do now. Is there any question for me? No? Okay. Now let's see what is upcoming then. What is in the next class? Sure.
Oh wait, I actually have a question.
Yes.
Are these lectures posted on your YouTube channel or on Canvas somewhere? Sorry, I forgot.
YouTube channel, yes. I usually update the pages of the recording as well.
Okay.
Yeah.
Okay, thank you. Yeah.
Okay. Okay, so this is your page look like, your home page. Let's go to the syllabus and see what is upcoming. Next day means August 30. So the August 29 I'm looking at. So you need to look at the lecture 2, computer organization. So I give you a sneak peek of today's lecture, like how the computer system work. We'll learn them in detail in this lecture. What we have? Okay, we have ALU clock system models. This is the one I haven't told you. This is one of the important concepts that you need to grasp. This mainly says that first of all, you need to understand why the clock system is important for any computing system, and how this different component in the computer synchronizes their operation with respect to clock. Clock is basically heartbeat for any computing system. So please make sure you understand that model. And then on top of that, we'll discuss the memory system and its operation with respect to the clock. Like at each clock, at each time, what happens inside the memory, and some related concept. This is a little bit complex. So if you are not comfortable first time watching the videos, please go through them again. Ask me questions on the discussion, and we'll discuss it next day about your conception difficulties. If you have any, prepare a lot of questions for me for next day. All right. And then register file model. Here, I'm going to explain how a generic memory system model can be reduced into register file model, and what is the purpose of the register file model. And then control unit model will touch base on these and 5-stage operation, how the control system works. But we'll more focus on this control system model on computer architecture study. This is just for an FYI kind of part for you to understand rest of the system and has a bird's eye view on the whole topic. And it has quite a lot of different parts, like 6 parts of these whole lecture videos. So make sure you assign proper time to watch it, note down your questions, and we'll discuss in the next day about this. All right. So that's all I have for you today. Unless you have more questions for me, we can stop tonight and leave early. No, not any question. All right then.